Okay, we're going to learn how to multiply or show you how to multiply two digits by two digits. Basically what I mean by that is like 34 times 27. So two digits times two digits. To do this again, we're going to use the idea of groups. In this case, there's 34 groups of 27 or 27 groups of 34. And that the students know how to multiply one digit times two. In other words, they know how to multiply 4 times 27. Okay, so they have to know that prior to two digit times two digit. Typically, two digit times two digit is shown maybe a little bit in third grade, fourth and fifth grades when it's really built upon, especially fourth grade. To begin this, we want to begin with a pattern. So to prepare for that, two digit times two digit, we're going to do do an exploration like this. 2 times 34, and of course this is 1 times 2 digits. The students can do this without a calculator. But for the next one, we're going to want the students to use a calculator because this is a 2 digits times 2 digits, and they really don't know how to do this, right now. So we're going to use a calculator. It's an excellent tool for us to help students explore. We're gathering data, which we're going to write on the board and let the students find a pattern. Okay, so 20 times 34, I'd have the students do that in the calculator. And I write that on the board along with 2 times 34. And I say, okay, again, use the calculator, 200 times 34. And I'm starting to see some similarities there. And so based upon this, I could ask the students without a calculator what they thought 2,000 times 34 is going to be. It's not going to be too hard for them to say 68 with 1, 2, 3, 68,000, or 68 with 3 zeros. I could ask them, well, where do you see that? They're getting it from here. Okay, so they just created a way to multiply this without using a calculator, without actually having to use any kind of written technique. Okay, there's the highest levels of Bloom's creation. Okay, then I could have them check it with the calculator, and the thing worked. All right, so maybe we try another one. I ask them what's 3 times 41, and that they can do without a calculator. And they find it's 123. And now I'm going to use a calculator to help me gather more data, which I'm putting all on the board. 30 times 41. And they use the calculator. And things are starting to look kind of similar to the last problem. 300 times 41. They put it in the calculator. Well, it's not going to be too hard for them to come up with a reasonable guess for what 3,000 times 41 is going to be. It looks like it's going to be the same as 3 times 41, 123, with 1, 2, 3 zeros on the end. Okay, 123,000. They make that guess. I write it on the board. Then they go back to their calculator, they check it, and this thing works. So it looks like as long as I'm multiplying a 10 or 100 or 1,000 times a two-digit number, I can figure out the answer by just multiplying one digit times that same two-digit number, and then just putting a bunch of zeros on the end, depending on how many zeros I have to put on the end here. Okay? So we could test that out with a few problems. I could have them try like 5,000 times 13 and say, what do you think the answer is going to be? Well, it looks like 5 times 13 with 1, 2, 3 zeros on the end. Let's see, 5 times 13. They already know how to do this, 1 digit times 2. So it's going to be 65 with 3 zeros on the end. Okay? So that skill right there, that's a whole lesson in and of itself. Okay. They've got to know that before we go on to our 2-digit times 2-digit multiplication. So we talked about groups. And so here we have, let's say we're going to start with 23 times 34. So it's 23 groups of 34. Now, I would love to use the base 10 blocks, because you imagine me trying to make 23 groups of 34, having all the students make 23 groups of 34. That's a lot of blocks to begin with, and that's going to be a lot of time to create 23 groups of 34. Okay? So rather than use a concrete model, I think I'm going to use a semi-concrete model. So I'll give the students graph paper, color in 23 groups of 34. So here's one group of 34. So there's 23 of them. Okay, so once they have that, I'm going to ask them, do they see 20 groups of 34? And the answer is, well, there's 6, 12, 18, 19. There's 20. Yeah, I do see 20 groups of 34. So for those 20 groups of 34, how do I write that mathematically? 20 times 34. Okay, and can I solve that problem right now to figure out how many of those squares I have colored in of the 20 of the 20 groups of 34? And the answer is, well, yeah, it's 2 times 34 with a 0 on the end. So 680 squares here are colored in outside of the ones that are squared in here. Okay, so there's 20 groups of 34. Do I see 3 groups of 34? Yeah, the ones that are left here, which I highlighted with pink, are 3. And could I figure out how many little squares there are there? I don't have to count them all up. Imagine counting all these up. No, I could just use my multiplication. If it's 3 groups of 24, it's 3 times 34. Okay, and that they know how to do already prior to this lesson. And that was from the pattern that we did prior to what we're doing right here now. Okay, so I can take those over here and I have them do the 1 times 2 multiplication first and put that down, and then the 10 and put that down. So if I figured out what 20 of these have and what 3 of these have, then 23 of these would be adding those together. 782 little squares I must have colored in here. All right. What I've just done is I've taken this problem and used, again, partial products. I've broken this into 2 problems, and because I can solve these 2 problems here. I can't solve this problem right now, at least not in a purely abstract written way. I have to rewrite the problems into 2 forms that I can solve abstractly, and then I can just add them up underneath there. Okay, so this is partial products again. All right. Now, what allowed me to go from here to here, at least in the student's mind, is I was able to see it in a semi-concrete way. This is important, because if I just say to the students, I'm going to rewrite this as these 2 problems, they aren't going to necessarily believe that this is the same as those 2 combined. Why would they? It'd be very strange. You mean you can just rewrite a multiplication problem like that? What allows you to do that? I don't understand. As soon as they don't understand, guess what? They're back to memorizing. Math becomes something I can't figure out. I always have to memorize it. And if I have to memorize this and memorize all the other things in math, when it comes to taking a test, I start to get nervous because there's so much to memorize, math anxiety. And that's where it comes from. This alleviates it. So now, because of this exercise here, I see how I can take this, draw a picture, and turn it into that. Okay? All right, and now I believe that this is the same as this. Okay, I could do the same thing for a number of problems, and I would. I'd want to take a number of problems, such as, we'll just say 14 times 25, which would be 14 groups of 25, color in 14 groups of 25. I'd say I'd have 10 groups of 25, which I could write like this. And I'd have 4 groups of 25, which I could write like this. I could solve this one. I can solve this one and bring these numbers over here. Again, I'm going to bring the 1 digit times 2 first, and then the 10 Okay? I could put this on the board, this on the board, put a third problem on the board. All these are generated making a semi-concrete model. Now I would challenge the students. Is there some way I could have found these two problems from this problem without making a drawing? Or these two problems from this one without making a drawing? Well, by having 2, 3, or 4 of these on the board, the students have enough data that they can start examining it, analyzing it. Think of Bloom's analysis. They could come up with, see a pattern in there. When they see a pattern, they created it, which means highest levels of Bloom's creation. And then we can test it. Okay, so we can evaluate that pattern. Again, very high levels of Bloom's. The students are coming up with these ideas. I'm just guiding them. All right. So if they might look here and they might say, oh, it looks like you can always just take whatever in the ones digit and multiply that. The ones digit of this one here, multiply by that number, and then just use that with a 0 on the end, this with a 0 on the end. Okay, so then we would test it. So now for the first time abstractly, we're going to do a partial products method to solving this problem. So I can give them one for the first time where they aren't going to make a drawing, but they could make a drawing to check it. Okay, so it looks like, well, I could make this into 20 times 18 and 5 times 18. That's the partial products. Solve it here. Bring it over here. Okay, and then if they need to, they can check it by filling in some more grids and seeing, does it really work? Did I go from here to here? Okay. Rather than asking the teacher, did I do it right? I'd say, well, go ahead and check it. You tell me if you did it right. Always empowering the students, letting them know that they can do it by my actions and my words, saying, well, you show me. Okay? If they did make a mistake, they'll find it, or at least have a good chance of finding it. Again, empowering them. Math makes sense to them. They can figure out these things. Okay, so now we have a procedure where they've learned how they can take a problem, a 2-digit times 2-digit, turn it into 2 other problems called partial products, solve those 2 problems there, bring them over here and solve the big problem, the overall problem. Okay? So I'd let them, that'd be the end of the lesson for the day. Let them do this a few times, and then there's going to maybe do this another time for another lesson or practice. And then there comes a point where I'm going to challenge them. I'm going to say, okay, you always had to take this problem and write it into 2 problems. Could you have just done it all in one problem here rather than rewriting it? Could you have done these 2 problems over here? Can anybody figure out a way to do that? Course. Well, the idea is I could do the 5 times 18 by ignoring the 20 part of the 25 and multiplying 5 times 18 and getting 90. And then ignore the 5 part, think of it as a 0 there, and multiplying 2 times 18 with a 0 on the end. Oh, I could do this all here without rewriting it here. Okay, so we would test that and let them try a few problems like that. Maybe I'd have a set of homework problems that they could check their work with. Maybe a set of homework problems that they did where they took up one problem and broke it into 2. And now that they're trying to do it all at once, they can go back and look at their homework problems and to evaluate this method. And sure enough, it's going to work. So now they don't have to rewrite the problem. And that's it. This is the way we do it here. Okay? But we arrived at this method of solution for the students. They've built it. They came up with it. We're facilitating it. They're understanding the concept. It's going from a semi-concrete to an abstract way of solving the problem.